Hello, we're back on the channel here in Davos. I'm here with the esteemed David Siegel. David, man of many hats. No hats right now, but of many hats. You're on the executive committee of MIT, the MIT board. You're the co-founder of 2 Sigma, co-chairman now also of 2 Sigma, and also one of our investors at SandboxAQ. Let's start talking about AI itself. You've been somebody who's been thinking about AI and using AI, and advanced compute at 2 Sigma for decades. When we think about AI, a lot of people still focus on language AI, but there's a whole nother part of AI that is really about AI for science. You and I both have a passion for chemistry, biology, physics, and these kind of discovery areas. Talk about that kind of AI. Talk about your perspective on AI for science.
Well, the scientific fields have benefited from computers for a long time. Imagine science today without a computer. It couldn't be conducted. And the scientific progress has really accelerated with the introduction of computing. AI is a continuation of this. I don't think of AI as magic. AI is something that's evolved for decades and decades and decades. And scientists, of course, want to use the very best technologies to advance their fields. The wonders of AI are that it's essentially a new class of algorithms. People are focused, as you said, on the generative AI aspects. Another part of AI is on making predictions, looking for patterns in data, taking
quantitative data, making predictions from that.
And to find things in the quantitative, this is what scientists do all the time. But AI is actually a way to turbocharge this skill that scientists have really used since pretty much the beginning of science.
Yeah, and when we think about, for example, in chemistry and in developing new medicines, we know the equations that govern chemical interactions down to the subatomic level. We can use those to actually generate new data itself. One of the big differences in quantitative versus the language side is language has to use the corpus that's out there, the big corpus of words out there. But in the quantitative side in science, we actually have equations that can generate 100 million versions of a particular molecule with small changes. That forms a new kind of training set. A training set is generated itself. Talk to us about synthetic data, the idea that you can actually generate pristine data from equations.
Well, most of the data that we have in the world is fairly narrowly focused. Part of it is that it's kind of hard to collect data. It's actually very expensive to collect data. For some endeavors, it makes sense to undergo. So, for example, for climate science, the field has been advanced for a long time by more data and micro collection of data.
Yeah.
And it allows you to get, maybe not understand the model, but it allows you to at least see the relationships itself amongst the data. Now, in other domains, the lack of data could be enhanced, as you say, by actually using models to generate it, and then AI can be used to then look for the relationships
and
patterns
from there. Yeah.
and optimize off of this generated data. It's a little bit challenging because you have to make sure that the data that you're generating is truly representative of the problem that you're trying to solve. But that being said, these methods are being used with increasing success.
So David, now let's turn to the other hat, the MIT hat. You're one of the leaders on the board of MIT. You think very deeply about how do we train the next cohorts of not only undergrads, but also masters and PhDs and postdocs. We at SandboxAQ have a residency program with MIT. We accept a number of students every year, and we co-train them in real projects in the real world, in biology, in chemistry, in physics, before we return them back to MIT. How do you think about this interplay between industry and university in training these advanced, skilled individuals?
Well, I think one important thing to reflect on in science is that it's not all about just AI. Science is a bunch of different fields with a lot of specialized knowledge. Universities are really the place where people develop these skills in the fields that you just mentioned and many more. And so I think one of the advantages of these sorts of partnerships is that we can encourage the development of students who are interested, for example, in material science and AI together. And the future, I think, of scientific research is in this kind of interdisciplinary collaboration, and increasingly the collaboration must occur in partnership with industry. No one can do it alone.
Yeah, agreed. One of the things you and I are both passionate about is the underlying queen of sciences, as it's called, which is mathematics itself. I was able to hide and squeeze a math textbook inside my quantum textbook because it's a Springer book, so the Springer people like math a lot. You and I both share that passion. What are your visions about how do we bring math back as an exciting subject for students? It's been something that many students are afraid of or intimidated by. What are your thoughts about that?
Well, I think people find AI to be very exciting, right? AI is math.
So just call it AI and they'll get excited.
Exactly.
Okay, got it.
Yeah, the thing is, you and I have talked about this quite a bit. Math is absolutely everywhere.
Yeah.
And maybe if you just talk about math for math's sake, that's not the right way to frame it.
Right. So we maybe talk about in other contexts, people can get more.
And the same, by the way, goes for computing. It used to be people were interested in computing for computing's sake and AI for AI's sake. What we need to do is to get people to move to science is a really great endeavor. Tools like AI, math, and many other things will turbocharge these fields. We have to get people on board with that.
Let me talk finally about OpenAthena. This is a brainchild of yours. You have a number of partners coming together to make this happen. What is it? What are the goals?
One of the challenges with the adoption of AI in academic environments, for example, in a chemistry department or a biology department or a climate science department, is that these departments don't really understand how to build software. Building software, the engineering behind building scientific software,
It's a different discipline.
It's totally different. And it turns out it's actually hard to do, and it's really important to do. What OpenAthena is creating, it's a nonprofit, we're essentially a software engineering company that will be providing software engineers and software libraries and APIs to scientific projects.
It'll be open source?
Entirely open source, and done in a collaborative way, trying to build research teams, bring research teams together at different universities, and to try to essentially narrow the gap here so that if you're a biologist and you want to apply AI and AI approaches to your work, which they all want to do now, they'll actually be able to do it.
Right. So if I'm a particle physicist, a physicist at a university or at CERN, I could turn to OpenAthena, collaborate, and together we can create libraries that would help me interpret these interactions that we
and in many cases, what we want to do is to actually provide software engineers to your team. And we're going to do this in a way that is essentially almost like a collaboration, meaning the software engineer will feel like they're part of your research team, but they're also going to feel like they're part of OpenAthena and have a career as a research software engineer.
Great. Well, David, great to be here today. Excellent to collaborate, as always.
Thank you, Jack.
Thank you, David.